This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301, statics. We've got a problem here, moment of inertia by integration, and in this case we have a y-axis boundary to our shape, and so we're going to use a horizontal strip. So the shape is, as I've shown sort of shaded here, it goes from, on the y-axis, from 1 to 4, which as I say is a boundary. The curve here on the left, on the right side, is y is equal to x squared over 3. I can rearrange that and I can say that x is equal to the square root of 3 times y to the 1/2 power. So the goal is to find Ix and Iy, the moments of inertia about those two axes. So we're going to start off doing Ix, and it's based on the basic equation that Ix is equal to the integral of y tilde squared dA. Okay, so looking at the shape, dA, as I've shown in red, is a rectangle, a horizontal rectangle, with a base of x and a height of dy. Therefore, dA is x dy, just the area of a rectangle. Now, we can plug that into this expression for Ix, and we also note that I've drawn in blue that y tilde is y, whatever the y value is along that curve. That's what y tilde, the distance from the x-axis, is. So we can rewrite this expression as y squared, which is what y tilde is. Oops, I forgot a squared there, didn't I? Times dA, and dA is x, is a little rectangle, x by dy. So now we can start plugging in numbers that we know. We want to evaluate it from 1 to 4 along the y-axis. Well, y squared, just y squared, x is equal to that value that I just rearranged that curve equation for, and I get square root of 3 y to the 1/2 power and dy. So I can evaluate that as the square root of 3 and take it outside the integral. Y to the 1/2 times y squared is y to the 2.5 power. And once again, I'm going to evaluate it from 1 to 4. So I can evaluate that as equal to the square root of 3 over 3.5, y to the 3.5 power, evaluated from 1 to 4. At 1, it's equal to 0.4949. At 4, it's equal to 63.34. Subtract those from each other, and I get 62.85. My units are inches to the 4th, because all these are in inches. Okay, so for Iy, for reasons of the parallel axis theorem, I can't evaluate it quite the same way. So I use what I sometimes call a trick. We know from other work that we've done, if I have a rectangle that is got a base of b and a height of h, the moment of inertia of a rectangle about an axis on its side is, in this case that would be a y-axis, and it would be b cubed h over 3. So in our case, that little rectangle is actually the differential element dA. And so b is equal to x and h is equal to dy. So I can say that the derivative of Iy, a little differential element, the derivative of Iy is x, which is b, x cubed divided by 3 times dy, which is h. That's what we're going to use. It's what I sometimes call a trick. It's not really, it's just a mathematical simplification That makes this problem easier to solve for. So Iy is going to be, instead of the integral of x tilde squared dA, we're going to say it's just the integral of that differential moment of inertia of a rectangle about an axis on its side, diy, which is equal to the integral from 1 to 4, because we're integrating on the y-axis, of x cubed over 3 dy, which I just derived from down there. So that's equal to the integral from 1 to 4. Well, x is equal to the square root of 3 times y to the 1/2 power. So I rearranged it up there. I've got to cube that and then divide by 3. And it's all with respect to dy. So that works out to be square root of 3 cubed is 5.196. Take the third out of the integral, and it's the integral of y to the 1.5 power dy, which is equal to, do all the math, I get 1.732, which is 5.196 divided by 3. Now divided by 2.5, because I'm evaluating that integral, y to the 2.5 power. Evaluated at 1 and 4. At 1 it evaluates to 0.6928. At 4 it evaluates to 21.17. Therefore the difference is, the answer, 21.48 inches to the fourth. So you see it's about 1/3 of what Ix is, because the distribution of the spread from the y-axis is a lot bigger than the spread from the x-axis.